Now, we are moving to our last session. For this session, our session chair is Sri Ramchandran P. He is Scientist G at the Office of CCA, Controller of Certifying Authority. In this last session, we have two papers. First, I would like to felicitate our session chair. So I request Dr. Balaji to felicitate our session chair.
Good evening, everyone. Myself, Dr. Noorul Hussain, from Interest Innovation Lab, IIT Madras Research Park, Chennai. Today I'm sharing our work, crash platform benchmarking for Shor's algorithm for quantum cryptanalysis. So far in the morning presentation, so we talk about the PQC and why we are moving about the PQC. So this kind of things we are seeing things. But actually, why all the cryptographic systems moving to the post-quantum signature? Because of the two algorithms. One is the Shor's and another one is the Grover's. So we are exploring, so many researchers, they have theoretically proved that Shor's is compromising the RSA and ECC algorithms. So we have to practically explore this by using the unlock the current capabilities of quantum computing framework tools. So moving to the next slide. These are the things, as we know that the foundation of current encryption is completely based on the difficulties of the factorization large numbers, that is the RSA and the ECC for the other systems safeguard the global communication. So now that systems are compromised using this Shor's algorithm. So that is the ultimate motivation for our research work. Moving to the next slide. So to understanding the Shor's algorithm, it is a hybrid process. First, we have to start with some classical pre-processing, then uses the quantum computation for the core pre-at finding steps, and finally finishes with the classical post processing to extract the factors. The real power lies in the quantum Fourier transform that accelerates the pre-at finding part, giving the exponential speed up over classical factoring. So this is the quantum Fourier transform with the key role to speed up this quantum pre-at finding subroutine for the searching the Shor's algorithm towards the RSA and other ECC other algorithms. So moving to the next slide. So these are the tools in our study. We benchmarked 7 popular quantum computing tools. One is the Qiskit. Qiskit and Google Circuit, which focus on hardware integration to symbolic or hybrid frameworks like Pennylean and Qtip, which emphasize the scalability and simulation. So the idea was to see how these platforms performs when task running with the Shor's algorithm. So moving to the next slide. So this is the diverse ecosystem of the quantum computing framework. So each framework brings unique strength. Qiskit offers direct integration with IBM's quantum hardware. Circuit allows fine-grained circuit control. Pennylean enables the hybrid quantum classical workflows, especially in the machine learning, and Qtip specialization in the symbolic quantum dynamics. Project IQ and Tequila and Cuba each have their own optimization. So together they represent the diversity today's quantum ecosystems. So we have, moving to the next slide, we see about the how our experimental methodology. So in the right side, we see our Shor's implementation flow chart. And to keep our study, to narrow down, we use the same methodology across all the framework. So we factored integers ranging from the up to 15 digit we have taken for the 47-bit numbers. The workflow was consistent, validating the inputs, running the quantum order finding steps, and extracting the factors. So this is the way we could compare the framework under similar conditions of our experiment. So moving to the next slide. So these are our results. Penilyn achieved the best outcome of the 60 qubits with the maximum of the 15 digits. So this is the current capability of in the software capability. So in IBM, they have in one of the Chinese papers in the hardware level, in the real quantum computing, they have compromised 22 bits for the RSA. So we have to reach 4096. For software level, we have reached the 15 digits, that is a 120 bit approximately. So in order to achieve a 4096, we need at least more than 512 bits ranging. That is the 512 digits. So Qiskit and Circuit, which are closer to hardware implementation, only managed 4-digit numbers. This clearly shows that symbolic or hybrid approach are better at scaling, at least in simulation level. So moving to the next slide. So these are the performance analysis of the heat map. When we compare execution times, Penilyn and Cubar consistently performed faster. Qiskit showed moderate growth in runtime as a problem size increased. So Circuit, however, scaled poorly, was the slowest overall. So these performance differences highlight the not all the framework are equally suited for the large scale cryptanalysis simulations. So moving to the next slide, we see the insights of the trade-off, fidelity with scalability. So the key takeaway here is the trade-off. Gate level simulation like Qiskit or Google Circuit, IBM's Qiskit are accurate but do not scale well. When it comes to the symbolic approaches like Penilyn and Q-tip, create scale efficiently but are less tied to the hardware precision. So both are important. One gives speed, other gives the realism. So this is the different in the trade-off. So moving to the next slide, based on this analysis, we have introducing our quantum efficiency index. So this is the novel metric benchmark. To capture this trade-off, we have introduced this called quantum efficiency index. So this balance the success rate, maximum bit length factored, qubit used, and circuit depth. So rather than just measuring the speed size alone, we have introducing the QEI gives a holistic measure of efficiency. How to we have to measure the values in this software and in future in our future work in the hardware level also. And so these are the results in the QEI. We see the Penilyn fare with a height of 0.0039, and when compared to the gate level simulator, which average around the 0.0005. So this confirms that hybrid framework are more efficient for exploring the Shor's algorithm at large scales, while gate level tools lags behind. So that is the IBM Qiskit and as well as the Google Circuit. So moving to the slide, our conclusion. So key takeaway of our discussions, to summarize, symbolic framework excels when scale and speed matters. Gate level framework remain essential for hardware readiness, but overall modular expansion and qubit demand are still bottleneck actually. So our proposed workflow is combining both symbolic simulation and quick exploration of gate level for circuit validation, and then we are planning for the hardware testing on small real devices. That is our future work. Thank you for your attention. I hope this will help in the more contributing in this space in the community of cryptanalysis, and I'd be happy to take your questions. Thank you. Ah. Digit. Yeah. Yeah. We have to compare with the RSA only. We have taken the values of the RSA 496 here. So that is in our complete experiment, RSA 496 is the benchmarking we have taken. So that is the results we have shown here. So that is the digit based. In some paper, author says that 651 digit. So it takes more time, but our current capabilities that lacks actually. Only 15 digit we have to run it. So that take much time actually. So we have to increase our high-speed computers, high-speed performance also. So that we have to compare with these things in the software level testing. Now we are moving in our future work. We have 3 things we are planning. One is the gate level simulation, hardware testing, that is the cloud backend, and QPU in noisy environment. So noisy environment is there is a limitation here. Noise-free simulators we need to test in the we have to increase the digits, and then we have to, this is our continuous development work. Extent of this work we have presenting next year in the ICER journals. Yeah, it depends upon the maturity of the cryptographically relevant quantum computer, not quantum computer, ordinary quantum computer. Cryptographically relevant quantum computer will perform this kind of tasks for compromising the RSA, ECC by using the Shors and Groovers. Groovers will weaken the key size. It's not broken, it's weakened actually. Weaken, if it is 128, it will weaken to 664. And for AES, the Simon algorithm is there actually. So that will compromise the AES in future. AES is not affected still, but researchers are a lot of papers what they are talking about. Simon is possible to weaken the AES keys. Currently we using the lightweight environment AES 128 bit. So that will be weakened into 64. So that can be weakened. So any other questions, sir? Yeah, thank you. Thank you.